sure if this is working. If it has started working, wonderful. I'll start off with the thing directly. Hello YouTube. I'm going to be checking first if it is started officially. This is the first time I'm experimenting on streaming. So yeah, should check. Alright, it seems to be starting off soon anyway, so let me start it off straight away. Yeah, hello YouTube, thank you very much for streaming in. Today we are going to be discussing the chemistry paper. Okay, I need to add an audio source as well. Alright, things seem to be working properly. Just tested it out as well. So let me start it off directly. Thank you for streaming in. So let me start off with the JEE Mains paper 1 on 21st of January 2026, shift 1. Okay, so this is the paper which I have basically acquired from well, some of the reputed places in the industry who post out question papers regularly. So this is mainly a mix from both Allen and Akash Institute's question papers which they have posted on their websites. So let's start off with the discussion of the questions here and see how the paper is going today. So in this here we are going to be having the first question here looks like this. So we're going to be having PbCl2 plus K2CrO4 is going to be giving me A plus KCl. So that is going to be of course something where A is going to be nothing but PbCrO4, which is going to be a yellow color precipitate. So this is going to be a yellow color precipitate over here, and we are going to be having that is going to be then treated with well, sodium hydroxide excess. So when you're going to be reacting this with sodium hydroxide excess, now initially sodium hydroxide is going to be reacting with the lead over here to form lead hydroxide or sometimes lead oxide as well. But when you're going to be hitting it with excess sodium hydroxide, lead is going to be something which is an amphoteric system, especially in the form of +2 oxidation state here. It is amphoteric, so it will dissolve to form PbOH4 times 2 minus. So this will end up forming PbOH4 times 2 minus as the complex which is formed over here, and it will dissolve over here. Okay, next up what we're going to be having is we're going to be having a separate reaction given over here where we are going to be having PbSO4 is going to be reacted with ammonium acetate in this case here. This is one of the few substances or few solutions in which PbSO4 actually dissolves. In the sense PbSO4 is something which is highly insoluble and doesn't dissolve that easily. So one of the few things in which it actually dissolves is going to be ammonium acetate solution. What does it actually form? It ends up forming lead acetate as the product over here. So you're going to be having this as an aqueous compound over here. It is going to be dissolving into it, and you'll end up having, in this particular case here, what are A, B and C? A is going to be this compound over here, which is my PbCrO4, which is going to be yellow precipitate. B is going to be my complex over here, and C is going to be this fellow here. So which means the correct option here will work out as A is PbCrO4, Na2 PbOH4 times 2 minus, and we'll PbOH4 times and PbCH3CO twice. So we'll end up having the correct answer for this being option 2 in this particular case, which is technically what they have given in the key as well. So it seems to be correct over here. Let's go for the next one here. So the next question is going to be this one here. Among the following compounds, there are 3 tetrahedral species. This is a statement 1 and it is a statement 2. So it's an assertion reasoning type of question. Not exactly assertion reasoning. Statement 1, statement 2, where they're asking which ones are going to be correct, etc. based on that. So we're going to be having, among these, there are 3 tetrahedral species. So let's quickly have a look at the 3 compounds over here and see what exactly are the 3 tetrahedral species over here. So in this particular case here, the three compounds which are going to be tetrahedral. So tetrahedral means you're going to be having sp3 hybridization taken into account over here. So if it's supposed to be sp3 hybridization here, let's have a look. SF4 is going to be something which is going to be having one lone pair. So this is sp3d. So this is going to be an sp3d hybridized. XCF4 is going to be having two lone pairs. So this is sp3d2. Okay, I might as well put it out separately over here. NiCl4 times 2 minus. This is going to be sp3. This is going to be a nice tetrahedral complex. PtCl4 times 2 minus. Now, one important thing to pay attention to here is this. All platinum complexes, all platinum 2 plus complexes are going to be either square planar or they are going to be octahedral. Octahedral in the sense, if they are going to be having a coordination number of 6, they are going to be working out as octahedral. If they have a coordination number of 4, they are going to be square planar. So this is going to be a DSP2 type complex. It is not going to be sp3. So both this and PtCN4 times 2 minus are both going to be DSP2 in this case here. Now, how do we know, how do we arrive at each of these over here? Very straightforward type of thing you can do over here. Yeah, you can memorize it or you can understand or remember it like what I just used over here. But the reality is remembering is not that straightforward or simple actually. So you'll have to basically go for the basics over there. So when you're going to be looking at nickel, in this case here, whether it is NiCl4 times 2 minus or NiCN4 times 2 minus, it is actually nickel plus 2. Nickel plus 2 is going to be a D8 type of system. So you're going to be having nickel, palladium and platinum. Platinum 2 plus is also going to be D8. Now when you're going to be having D8 configuration here, you're going to be having both sp3 and dsp2 being possible. So for the nickel plus 2 here, it will end up forming sp3 with weak ligands. And the nickel plus 2 will go for dsp2 with strong ligands. Whereas the platinum 2 plus will only end up forming proper dsp2 complexes whether or not it is going to be strong or weak. So platinum 2 plus is going to be always dsp2 if it is going to be having coordination number 4. Okay, so in this particular case here, we are going to be having which ones are going to be sp3 here. sp3 so far we have had only one of these guys as sp3 here. We are not going to be having any of the others as sp3. Let me just check out if the stream is working properly. Just confirming how it is coming out. Alright, it seems to be rolling along, so continuing on. Okay, so it seems to be rolling along comfortably over here. So let me just continue on with this over here. So in this particular case here, you're going to be having PtCN4 times 2 minus and NiCN4 times 2 minus. Both are going to be, what to say, cyanide is going to be a strong ligand over here. So cyanide is going to be a strong ligand and chloride is going to be a weak ligand. So you're going to be having Cl minus being a weak ligand, cyanide is going to be a strong ligand. So with the cyanide in this particular case here, NiCN4 times 2 minus is going to be a proper strong ligand, meaning you're going to be having this also as dsp2. Okay, so this is also going to be a dsp2 here. It is not going to be sp3. SeF4 is going to be selenium. Selenium is going to be an oxygen family, so it is going to be similar to your sulfur. It is not going to be similar to anything else. It's going to be similar to sulfur, so it's going to be sp3d2. So you're going to be having 3 tetrahedral species here. This statement is wrong. Alright, this statement is wrong. There are not 3. There is only 1 tetrahedral species in this actually. So this part is wrong. It is actually supposed to be 1. Okay, so statement 1 is going to be wrong in this particular case here. So that directly gives us an option here which is going to be possible. So it can either be option 3 or option 4. So we are going to be directly ruling out the first and second options here. Now among the 3 pairs here, these 3 pairs, only 2 pairs are diamagnetic. Now when it comes to diamagnetic nature here, you're going to be having D8 in sp3. If I have nickel 2 plus, all of these are nickel 2 plus complexes here. Nickel 2 plus, actually not all of these, NiCO4 is nickel 0 here, whereas the others are all nickel 2 plus here. So this is nickel 2 plus, this is going to be nickel 2 plus, this is going to be nickel 2 plus, and this is also going to be nickel 2 plus. So when you're going to be having these as the different pairs here, nickel 2 plus D8 with sp3, in the sense if it's going to be a weak field, then it is going to be paramagnetic. If it goes off for a dsp2, then it is going to be diamagnetic. So in this particular case here, which ones are going to be diamagnetic here? We'll end up having the nickel D10 here. Nickel 2 plus is going to be D8. So nickel 0, I should not have written it on the corner there. That is something to learn for the next live stream. Okay, nickel 0 is going to be a D10, and that is going to be diamagnetic in DsP2 configuration. In this particular case here, what are we going to be having here? We are going to be having among these three pairs, which ones are diamagnetic here? Diamagnetic is NiCO4, which is diamagnetic. This one is not. This one is diamagnetic. This one is diamagnetic. This is diamagnetic. This is not. So among this here, the only pair which is diamagnetic is this one over here. So this pair is diamagnetic. So only one pair is diamagnetic. So this is also wrong. So answer is supposed to be only one. So both statements are incorrect over here. So technically speaking, we are going to be having this statement being correct. This is wrong. This is wrong. And we are going to be having in this particular case here, the correct answer is going to be both statements are incorrect in this particular case here. All right. So this page did not go out very well because I have not really planned it out perfectly. So let's go for the next one here. This should work out comfortably. It seems like a very straightforward and easy and simple question. MnO4 minus 2 in acidic medium disproportionates to. So this is a very straightforward disproportionation reaction. MnO4 minus 2 is in +6 oxidation state here. When it is going to be in acidic medium, it will disproportionate to its next higher and its lower oxidation state, which are very stable. So in this case here, you will end up having it becoming MnO4 minus, and it will end up becoming MnO2, which comes out as a black PBT. It's a very straightforward question. So the answer has to be option 4 over here in this particular case here. Okay, next up. So in this case, again, there's a whole bunch of species here. So let me just make a quick copy of this page over here so that I don't need to, well, create a mess when I'm writing it over there. Okay, so in this particular case here, let's have a look now. So among NiCl 4 times 2 minus, NiCN 4 times 2 minus, NiCO4. So again, it's the same nickel complexes. So nickel 2 plus. The idea there is what? This is going to be a D8 configuration. So if it is a D8 configuration, you're going to be having 1, 2, 3, 4, 5 orbitals. And these are the 3D orbitals. This is going to be your 4s orbital. And we'll end up having the 3, 4p orbitals also available. So when you're going to be having it as a D8 configuration, so you're going to be having it originally in a form where if it's going to be a strong field ligand, it will pair up. If it is only in the presence of weak field ligands, there will be no pairing up happening. So when you're going to be having strong field ligand, what will happen is you will end up having it getting paired up like this. And you will end up having the ligand's electrons are going to be coming here, 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 and here, resulting in a nice DsP2 configuration. This will result in a DsP2 config. Whereas if I am going to be having, this is going to be in strong field, by the way. So this is for strong field or strong ligand. We can say it's going to be for a strong ligand. If it is going to be in the presence of a weak ligand, so let's put down the same 3D here. So this is going to be the 3D, this is going to be the 4s, and these are going to be the p orbitals over here. So 3D, 4s, and 4p. So if I'm going to be having a weak ligand, it cannot force enough repulsions to forcibly pair up the d orbital electrons there. So they will remain as they are, meaning we will end up having them in this fashion like this. So as of now, 7 electrons are put, so 8 electrons. So we're going to be having in this case, if it is going to be in a weak ligand over here, or weak ligands are present over there, you will have no options. The ligand's electrons will go over here S, and we'll end up having a P3 configuration fully. So this will be an sp3 configuration if it's going to be in the presence of a weak ligand over here. So this is the case in the presence of a weak ligand. So let's now have a look over here. Weak ligands, what are the examples for weak ligands? We'll have Cl minus, and yep, that's basically it. And this is going to be for D8 nickel 2 plus. If I was going to be having nickel in 0 oxidation state, this is going to be 4s2 3d8. Correct. So this is going to be technically capable of showing the ligand formation, or it can basically form coordinate covalent bonds only with strong ligands. So if it can form complexes only with strong ligands here, what does it really do? It will end up converting this into a D10S0. So it will become a D10, and then we'll end up having the 4S becoming 0, 4P will be 0. The ligands electrons will enter into this, and it will end up being an sp3 configuration in this particular case here. So when you're going to be having this working out as an sp3, yeah, it was fine. Yeah, so here it was not asking for structure for NiCO4 times. I just had to check that out once if I had done it correctly, because I remembered that there was NiCO4, but I didn't remember where it showed up really. So in this particular case, we are going to be having D10 basically working out over here for the nickel 0. So NiCO4 times is going to be a tetrahedral species over here. So if I'm considering NiCO4 times, this will be a tetrahedral complex, sp3. Okay, all right. So you're going to be having, which ones are going to be sp3 over here? So let's quickly have that look over here. So in this particular case, weak field ligand Cl minus. So NiCl4 times 2 minus. This will also be sp3, whereas NiCN4 times 2 minus. This will be square planar. Okay, all right. So what are the other sp3 species here? Methane is of course going to be sp3. So we are going to be having number of sp3 species or tetrahedral species are going to be 3, which is going to be NiCN4 times 2 minus. Not really. It is going to be NiCl4 times 2 minus, NiCO4 times 2 minus, NiCO4 and methane. These three are sp3 hybridized. So this statement is correct. So statement 1 is correct. That means Delhi we can already rule out as the option here, and we can also rule out option 3 also straight away over here. Okay, number of amphoteric pairs are. So yes, we are going to be having in this particular case here, which ones are amphoteric. So we'll have in this scenario here tin plus 2, tin plus 4, lead plus 2 and lead plus 4. All of these are going to be amphoteric. Now when it comes to germanium here, germanium is going to be above tin and lead. So germanium is going to be having much more acidic character. So germanium plus 4 is definitely acidic, no questions about it. Germanium plus 2 will show mainly acidic character, a little bit of basic character also it will show when it is reacting with a very very strong acid type of substance. So technically speaking, in this case, number of amphoteric pairs over here are, this is an amphoteric pair, that is my tin SNO and SNO2 are amphoteric, PbO and PbO2 are amphoteric. Why? Because it's plus 2 plus 4 plus 2 plus 4 plus 2 plus 4. GeO2 is definitely acidic, properly acidic, and germanium oxide plus 2 oxide is going to be showing mainly acidic character. A little bit of amphoteric character is also going to be seen, but technically speaking R3 is going to be wrong. Answer is supposed to be 2. So this pair is not going to be acidic here. So in this case, statement 1 is correct, statement 2 is incorrect. So answer has to be option 2 here. Okay. All right. So answer is option 2. Next question here. So this is also something which might go to the next page. So let me just duplicate this as well and keep it. Okay. So in this question here, we are going to be having all right. So which of the following is going to be, let me check if it's got another page. Yeah, it's got another page. I don't need to worry about writing too much over here now. So boron, sulfur, phosphorus and fluorine are going to be in terms of ionization energy. So let's say I'm comparing ionization energy here. Boron is going to be higher than sulfur. That is going to be something which is suspectable over here, because sulfur is going to be something which is going to be not having a proper half-filled configuration. Sulfur's electronic configuration, atomic number is going to be 16. So electronic configuration is going to be valence shell wise, it is going to be, which valence shell is going to be? It is going to be 3s2 and 3p4. So if it's going to be 3s2, 3p4, it is not going to be having a half filled over there. Whereas phosphorus, which is 15, will be having 3s2, 3p3 as the electronic configuration, meaning my p orbitals are going to be half filled here properly for phosphorus. Half filled means it's going to be a little bit more stable, little bit more difficult to remove the electrons from it. So we are going to be having automatically in this particular case here, the 3p electronic configuration is going to be half filled, means it will have higher ionization energy. So the correct order is supposed to be boron greater than phosphorus, greater than sulfur. Fluorine will definitely be higher than both of these guys because fluorine is in the second shell. So again, in this case here, this order is also not completely correct over here. We will generally end up having the correct order over here being a lot more complicated. So we'll end up having mostly the correct order should be something like this. Fluorine will be having the highest ionization energy, greater than the boron here probably, but they will be relatively comparable because fluorine is going to be very much on the end of the particular period over there, because ionization energy across the period should be increasing. But excepting in the cases where you're going to be having special electronic configurations coming up over there. So in this case here, between boron, phosphorus and sulfur, this should be the order. So this is definitely going to be wrong. So there's no meaning in checking this out beyond a point. So option 1 is definitely wrong. Next up, basic nature. Basic nature, and the third one is going to be metallic nature. Both of them are going to be something which are going to be very high on the left hand side of the periodic table. So basic, basic nature and metallic nature are effectively the same. So in this case here, this decreases across the period. So if it's going to be decreasing across the period here, from left to right, it is going to be decreasing. And of course, top to bottom, it increases. So you're going to be having decreasing across period, and simultaneously the other part over here is increases down the group. So it's going to be decreasing across the period and it is going to be increasing down the group over here. So in this scenario here, let's start plotting them. K2O greater than Na2O, this part is correct. MgO is going to be less than Na2O, mainly because it's going to be across the period for it. And Al2O3 is of course going to be partially amphoteric even. So yes, this order, option 2 is perfectly correct. Next one, potassium, sodium, aluminium and magnesium. This part is wrong over here. Aluminium and magnesium here. Magnesium is going to be definitely more metallic compared to aluminium. So in this particular case here, this part over here works out as wrong. So this option is wrong. Next up, chlorine, fluorine, sulfur and phosphorus. Effective, what to say, electron gain enthalpy is what is asked over here, or you can think of it as electron affinity. So in this scenario here, it is going to work in the reverse manner. When you're going to be having sulfur and phosphorus compared, what is going to be happening is sulfur. So I'm checking out for option 4 here, sulfur and phosphorus comparison. Sulfur is going to be having configuration as 3s2 3p4, whereas phosphorus is going to be having configuration as 3s2 3p3. So because phosphorus has already got a reasonably stable electronic configuration in the valence shell, especially half-filled p, it becomes a little bit more difficult for it to accept the next electron over there. Whereas the sulfur can accept the electron more conveniently in this particular case here. So you're going to be having this over here being correct over here. Now next part over here, chlorine and fluorine. Let's consider those two guys over here. So when you're going to be considering chlorine and fluorine over here, chlorine is going to be having lesser interelectronic repulsions, whereas fluorine has very, very small size. Yes, it is going to be having much higher electron negativity, but electron affinity wise, that is going to be an exception there, mainly because the extra repulsions, because of the very small size of the F minus, make it to have slightly lesser electron gain enthalpy or electron affinity compared to the chlorine. So in the halogen group there, you're going to be having chlorine being maximum, then fluorine, then we will end up having bromine and iodine in the same order here. So this is going to be the order in the halogens when it comes to electron affinity. So this order for option 4 is correct. So we had option 2 correct over there, option 4 is also correct. So correct answer is going to be 2 and 4 are both correct in this particular question here. Okay, next up. So I will need to copy this also into it because it's going to be requiring a lot of working, I suppose. So let me duplicate this once more. Okay, all right. So let's have a look at this question now. So in this particular question now, 14 grams of calcium metal is allowed to react with excess HCl at 1 atmosphere and 273 Kelvin. Which of the following statements is incorrect? This is going to be an irritating question, mainly because you have to solve and you have to check for each of the options, because definitely some of the options will end up working out as correct. So calcium metal is going to be reacting with excess HCl. What is going to be the reaction here? So it's a highly reactive metal reacting with a strong acid. So you'll have hydrogen gas being released over here. So hydrogen gas gets released, and we of course get calcium chloride obtained as the product over here. So in this case, we'll have 2 HCl balancing it out. This is the reaction here. So it's already in excess HCl, and they are clearly telling us we are going to be doing the reaction at 1 atmosphere pressure and 273 Kelvin. Okay, so they are giving us 14 grams of this is going to be reacting. Now calcium is going to be having atomic weight given over here nicely as 40. So if you're going to be having atomic weight given as 40, so technically speaking, this 14 grams works out as 14 by 40 moles. Alright, so let's calculate the value in moles over here. So it works out as 720. So 7 by 20. So 7 by 20 means 1 divided by 20 is 5% basically. So 7 is going to be 35%, or we can say it's going to be 0.35 moles. So let's start off over here. Limiting reagent is calcium metal. That is the easiest one. Yes, because you're going to be having HCl in excess over here. So limiting reagent is of course going to be the calcium metal only in this particular case here. So option 2 is definitely correct. So they are asking for incorrect over here. So this is correct over here. That means this is not the correct answer. Okay, next up. 0.35 moles of hydrogen gas is evolved over here. So look at the equation here. 1 mole of calcium is going to produce 1 mole of hydrogen gas. So 0.35 moles of calcium are involved over here. So I'll be having 0.35 moles of hydrogen gas also being produced in the reaction. So this statement is also correct over here. So this is going to be wrong as well. Okay, next up. Next up, they are asking us, there is another thing related to hydrogen gas. So let's go for that and finish it off. So 0.35 moles of hydrogen gas is produced. Correct. Now this is produced at what condition? It is produced at 1 atmosphere and 273 Kelvin. This is going to be my Avogadro's worth of conditions. So at this condition over here, 1 mole of hydrogen gas will effectively end up occupying 22.4 liters of volume. So if it's going to be occupying 22.4 liters volume, then we can now straight away proceed and say implies 0.35 moles of hydrogen gas should occupy 0.35. Now instead of putting it as 0.35, it is much more easier to shift it back to 7 by 20 because cancelling out is always easier. So 7 by 20 into 22.4. So we are going to be having in this particular case, let's divide this off by 2 over here so that it becomes 10 and it becomes easier for us to do the calculation. So 7 into 11.2. So 7 into 11.2 means we are going to be having divided by 10. 7 into 11 is going to be how much over there? It's going to be 77. So it's going to be 77 plus 1.4. Right? So it's going to be 78.4, entire thing divided by 10. So it's 78.4 by 10. So this works out as 7.84 liters. So it looks like this option is also going to be correct, which means this is also going to be wrong. So now let's have a quick look. So we have already eliminated out 3 of the options. So this is also wrong. This is also wrong. So answer should be option C. Let's just confirm it out once over here. 33.3 grams of calcium chloride is produced. So amount of calcium chloride produced. This should also be 0.35 moles. So you're going to be having this as 0.35 moles also according to the stoichiometry here. So if this is 0.35 moles, we can effectively say that calcium chloride produced is equal to 0.35 moles, which effectively means we can now calculate how many grams that is supposed to be. Calcium chloride molecular mass is going to be 40 plus 35.5 into 2, 71. So it's working out as 111. 111, yeah, correct, yeah, 111. So if it's going to be 111 over here, so we're going to be having 0.35 into 111. They are giving 33.3. Definitely this has to be greater than 0.35 into 100. 0.35 into 100 is 35. So this is greater than 0.35 into 100. Correct. 0.35 into 100 is going to be 35. So it has to be greater than 35. So definitely this option is wrong, which means this is the correct answer for the question where they are asking us which among the following statements is incorrect. Since they have asked incorrect, the correct answer here is going to be option 3. All the other 3 options are correct here. So there is only one option which is incorrect here. So it's a good question again. Okay, now let's look at this next one. This is an organic chemistry question. So we're going to be having consider the following reaction over here. So we're going to be having compound A. A good thing that I remembered now. Let me just duplicate this page as well. Okay, So consider the following reaction. We are going to be having compound A in this particular case here is going to be reacting with hydrogen and platinum to give me this compound over here, and it in the presence of hot alkaline KMnO4. Okay, they're asking which among the following will be compound A. So let's proceed on and get it done. So compound A, let's call this as reaction pathway 1. Let's call this reaction pathway 2. So in this case, let's look at okay, I should not have called them as reaction pathway 1 and 2 in that way. Let me use Roman numerals here so that it is more easier to change the thing. So I'm going to be calling this as reaction pathway Roman numeral 1, Roman numeral 2. So let's take compound 1. Compound 1 in Roman numeral 1. We are going to be having that being perfectly correct. You will have hydrogenation reaction only attacking this particular part here. So we'll end up having that basically giving you the product as option A is going to be correct over here. So we'll end up having the correct product obtained comfortably, no problems. Next up, in pathway 2 though, what is going to be happening there? We'll end up having in pathway 2 here, this will break. And this carbon will become carboxylic acid. This carbon will become carboxylic acid. So both of these guys end up becoming carboxylic acid here. But we are going to be having one more carbon present here. You're not going to be having them directly becoming carboxylic acid. So this does not work over here for pathway 2. So compound 1 pathway 2 is not going to be giving me that product. What does it give me? It gives me this product instead, where we are going to be having carbon COOH and another carbon and then a COOH. Meaning we are not getting this as the option here. So this part is wrong. So compound 1 is wrong. Okay. Compound 2. In this particular case here, you're not going to be having any problems over here. You're going to be having hot alkaline KMnO4 and H plus and H2O. There is one complication here which is unnecessary here, honestly speaking. Because technically speaking, if I'm going to be hitting it with hot KMnO4 here, what will be happening is there is a possibility that this also might break down. Because usually when I'm going to be hitting something like say a compound like this, let me just mention the controversy here slightly. If I'm going to be having say a compound like this reacted with hot KMnO4, alright, what happens in this particular case is you will be getting product as this one, carboxylic acid here. So in this particular case, there is a possibility that compound 1 is going to be giving, instead of this, if I treat this continuously, extended treatment with hot alkaline KMnO4, this has a very good chance of giving, well, the product which is given as the option over there. But the reality is also this, you're going to be having compound 2 being even better at giving the product here. This is going to be with hydrogen and platinum. Definitely it will give me this product. Compound 2 will be giving pathway 1 perfectly. Pathway 1 will work perfectly. And pathway 2 is also going to be working properly for this particular thing here, because you will end up having these two carbons directly breaking off over here because they are both having hydrogen. What is the principle there? As long as you are going to be having a benzene ring with a carbon attached and this carbon is going to be having a hydrogen present. If it has a hydrogen present, even one hydrogen, if you are going to be heating it in the presence of a powerful oxidizing agent, this will end up giving me benzoic acid. So the same logic applies. If I'm going to be having one more carbon over here, that will also end up becoming carboxylic acid over here. Meaning if I had another carbon here, that will also become a carboxylic acid. So technically speaking, both 1 and 2 are technically correct for this question here. It is a slightly ambiguous question here, but honestly speaking, we can't, if I have to pick over here in a JEE main setting, what will I be picking? I'll be picking option 2 as the correct answer. But in reality, is it just going to be option 2? Not really. Both option 1 and 2 are going to be correct here, according to this particular set of questions which have been given over here. There is always a chance that this is going to be something which is not properly remembered by the student, because this is basically from the student's memory. All right, so major institutes collect these things from students' memory and then make up the question papers. And yes, I have basically collected it from those major institutes and then I'm discussing the paper here. So in this case, there's a small bit of a controversy here. Both 1 and 2 are capable of giving the product, are fine as answer. But if it is a JEE mains kind of question, which is what this is, where we are supposed to pick only one option, if this showed up exactly as it is, pick 2 because it is less controversial. Now, why am I saying pick 2 over here? Very simply this, when you're going to be having controversy in a JEE mains paper, go with the general intention of the questioner over there. They are not trying to trick you there. They are trying to make sure that they are getting, what to say, the standard answer out. JEE mains is not something where they are trying to pull your leg on purpose over there. Especially when there's a more obvious answer, pick the more obvious answer. Avoid thinking too hard. Avoid going for the more complicated answer needlessly. So in this case here, I would say the best answer possible is going to be second option here for this particular question here. Okay, all right. So first option will also technically work out. I should not say first option is wrong here, mainly because first option, yes, it gives this as the product in the beginning, but that on prolonged exposure to an oxidizing agent will end up becoming the phthalic acid over here comfortably. This acid is called as phthalic acid. So you're going to be having this being a very, not very, slightly controversial question, but the best answer still is going to be option 2 over here. So pick option 2. Okay, now next up, this is going to be requiring definitely more than one page for sure. So let me add up a couple of pages. Okay, all right. So in this here, all right, okay, so 80 ml of an unknown gaseous hydrocarbon sparked in presence of 264 ml of oxygen gas. So this is going to be a eudiometry based question. So it's an unknown hydrocarbon. So let's say it's going to be something which is going to be, say, CXHY. So if I'm going to be having this unknown hydrocarbon over here, it is reacted with oxygen gas. Okay, they have clearly mentioned it's a hydrocarbon, so I'm not going to be adding any other component, any other elements over there. CXHY is sufficient, and they have given us this is going to be 264 ml. Okay, after complete combustion, gaseous mixture cooled down to 278 Kelvin and 1 atmosphere. Then its volume is equal to 224 ml in this particular case here. After passing the mixture through aqueous KOH, volume becomes 64 ml. Then formula of the hydrocarbon is going to be. So let's try to understand what is happening over here. We are going to be having 80 ml of this, and we are going to be having 264 ml of the oxygen gas here. So when you're going to be having full proper combustion happening here, so after complete combustion, the gaseous mixture is cooled down to this, and then its volume is equal to 224 ml. So what will be happening here is we'll end up having X moles of carbon dioxide produced over here, and we will end up having Y moles of water, or it's not really Y, it will be Y divided by 2, because you're going to be having each H2O molecule having 2 hydrogens there, so it's Y by 2 water. So if I have, say, this kind of a scenario here, how to interpret this, how do we read this? If I had 1 mole of this or 1 ml, why can I say 1 ml instead of 1 mole over here? Because the entire reaction mixture is going to be at a particular constant temperature and pressure condition. They are mentioning clearly what is the temperature and pressure condition. It doesn't matter what temperature or pressure condition, if I have pressure and temperature being maintained a constant. So what happens over there, we'll end up having PV is equal to nRT, correct? So if pressure and temperature are maintained a constant, then we can say V is equal to N into RT by P. So why am I putting RT by P? Because temperature and pressure are a constant here, maintained a constant. So I will end up having this entire RT by P term is also going to be a constant over here completely. So volume becomes directly proportional to N if P and T are constant. For the full reaction mixture. So in this particular case here, if I'm going to be measuring all of them at the same conditions, then I'm going to be having no problem. Volume, instead of writing it as volume, I can think of it as number of moles also. So moles wise, if I'm looking at it, what is the balancing over here from the oxygen's perspective? So we'll end up having X and 2 oxygens over here and 1 oxygen over here. So balancing for the oxygen over here will work out as X plus Y by 4. That is going to be the number of moles of oxygen necessary here. So for every 1 mole or 1 ml of CXHY needs, or it consumes, X plus Y by 4 ml of oxygen. Okay, So what is going to be left over for the oxygen here? We'll end up having 80 ml of this guy is being taken, correct? So we're going to be having not 1 ml of this, we're having 80 ml of this. So 80 ml of this means we'll technically be having 80 into x plus y by 4 ml is consumed. So what is going to be left over in this particular case for the oxygen over here? So leftover oxygen is going to be 264 minus 80 into x plus y by 4. I am of course assuming that the hydrocarbon is going to be completely consumed over here. That is the only way in which it can be a complete combustion of this gaseous mixture here. So I am making that assumption here that the hydrocarbon is a limiting reagent and we are going to be having perfect complete combustion happening here. Okay, so that means we are going to be having final mixture. What is going to be present there? We had x ml of carbon dioxide and y by 2 ml of water produced here. But pay attention here, water is going to be, it is at 278 Kelvin. This is where this temperature comes into play here. At 278 Kelvin, water is a liquid. It is not going to be a gas, it is going to be a liquid. So if it is a liquid, I should not be considering it as part of this over here. So in this case, this guy becomes a liquid, so I should not consider it. The gases are going to be leftover oxygen and carbon dioxide, which is produced over here, which is x ml. So we are going to be having final mixture here. What does it really contain? The final mixture now contains the following two things over here, which is going to be leftover oxygen, and we are also going to be having carbon dioxide gas. So how much is the carbon dioxide gas? X. How much is the leftover oxygen? 264 minus 80 into x plus y by 4. So this is my total volume finally. That volume they are giving us is equal to 224, right? So after passing the mixture through aqueous KOH, volume becomes 64 ml. This gives us our entire answer very easily over here. Why? Because what is going to be left over after passing through KOH over here? KOH absorbs acidic oxide. What is the acidic oxide among the leftover over here? In the leftover here, this is the leftover mixture, correct? In this leftover mixture here, it absorbs carbon dioxide. Meaning we are going to be having, after KOH, we will only have oxygen leftover. So if there's only oxygen leftover, that only oxygen leftover is going to be given clearly as 64 ml. Meaning I don't need to sit and do this full calculation over here. No need to do all that funny business here. We can directly proceed and get the thing done. So now what is the formula for the hydrocarbon is what they are asking. So we are going to be having, after it is done, 224 ml was basically the final mixture present. It became 64 ml. So x ml of carbon dioxide, what is that going to be here? That is going to be 224 minus 64, which works out as 160. So you're going to be having 160 here ml being produced when you are going to be having what here? When you are having 80 ml of that particular initial fellow taken there. So if it was 80 ml there, it is supposed to have been 80 into x, correct? Technically it should not have been, a small problem here. So it should have been 80 into x over there. Let me change the settings as well. Yeah, okay. So wrong one here. So coming back to the question. Yes, I have made a mistake here. This is supposed to have been 80 into x as well, not just x. So that's an error over here. So we are going to be having 80 into x over here, and this will also be 80 into y by 2. So we'll have 80 into x and 80 into y by 2 produced over here. So which is why I basically did the correct thing over here and put it as 80 into x plus y by 4 there. So that part I did correctly. Over here in this part here for carbon dioxide I made a mistake here. So this 80 into x is something which is now going to be equal to 224 minus 64, which of course works out as 160, meaning x works out as 2. So if x works out as 2, we are now unfortunately left up with 3 options over here, which we'll have to check here. So now when you are having 3 options to check, easiest way to proceed and solve it off is substitute in the oxygen over there and finish it off. After KOH, leftover is going to be only oxygen. Leftover is O2 only. and that is going to be 64 ml. So what is this new equation which we are going to be having here? This new equation works out as 264 minus 80 into x plus y by 4 is going to be equal to 64, and x is going to be equal to 2. So if x is going to be equal to, we can basically cancel off this over here. Oh, they have given none also as the option here. Very careful exam setter this time. They have not slipped up at all. So because they have not slipped up at all, we'll have to sit and solve this now again. No options at all. So if I'm solving for y over here, what do we end up getting? 264, 64. So we end up having 200 is going to be equal to 80 into 2 plus y divided by 4. So we end up having 200 by 80 or 20 by 8. So we can cancel this off 2, 5. So it's 5 by 2. So it works out as 2.5 is equal to 2 plus y by 4. So we are going to be having 0.5 is equal to y divided by 4. Meaning this basically translates as y is equal to 2. So if y is equal to 2, x is equal to 2. So answer is option 1. C2H2 is the compound in this particular case here. So this is basically how we proceed and solve here. So I had made a tiny error in the beginning when I was proceeding on. So please pay attention to that type of an error. That is going to be very much possible to happen. You need to make sure your stoichiometry is properly taken into account. Okay, alright. So this was this question. Let's go for this next one here. Alright. In sulfur estimation, 0.7 grams of an organic compound gives 1 gram of barium sulfate by Carius method. What is the percentage of sulfur in the compound? Okay, so 0.7 grams is giving me 1 gram of barium sulfate. So this is a fairly straightforward question actually. 1 gram of barium sulfate is produced here by Carius method. Okay, alright. Now this is a irritating question mainly because the barium here you need the, well, atomic mass for barium. Barium's atomic mass is not something which is given in the question over here. We will have to take a reasonable guess over here to get an approximation there. Now, luckily for us, they have given all these values at, well, good spacing over here. It is not that complicated here. So 1 gram of barium sulfate is produced over here. Barium is going to be calcium, strontium, and then barium, correct? So it's going to be calcium, strontium, and barium. It's before my D blocks, so not D block, before my F block starts off. So you're going to be having in this particular case here, barium atomic number. Let's figure that out first. So barium's atomic number is going to be calcium's atomic number, which is 20 plus 18 plus 18. So it's working out as 20 plus 36. So it's going to be 56. So it's 56 is the atomic number here. So usually around the level of, 30 plus, you'll have it as definitely double plus like 10 k aspas. So if you're going to be having it as double plus 10, what is going to be happening here? This is not the correct value of the barium's atomic mass there. So we are going to be having to approximate over here. Ideally in this kind of a question, the atomic mass for barium should have been given in the question. But well, things happen and they have not given us the atomic mass here for barium. So we can't do much over here. You can memorize whatever approximation they have used in Carius estimation in your NCRT and proceed also. But memorizing is going to be always more complicated. Avoid memorizing when possible. It is not going to be worth it beyond a point. Because chemistry always anyways requires you to remember a lot. And if you have to remember unnecessary numbers, it just gets too complicated. It is just not worth it. So 56 into 2 works out as 112. So let's say barium atomic mass. Let me add like say another 10 to 15 percentage. So 10 to 15 percentage, let's make it as 100. And so it's going to be approximately, this is not a sure answer. I'm just guessing over here. This is going to be an approximation only. So approximate atomic mass is going to be 112 plus another maybe 15. So 112 plus 15 works out as 127-ish. So it should be around 127, 128, 125 to 130. That is going to be the approximate range in which it is going to be present. So 125 to 130. So that is a reasonable estimation, I feel. I'm not 100% sure still. Let me just check up what is the exact atomic mass. Why not? Because ultimately, maybe in the JEE mains paper, they did give the proper atomic mass there. So okay, so it's 137. So I had made a mistake in the addition over there, probably over here. No, I have not. I should have added a lot more over here. So it's 137. So it's not 127, it is actually 137. So I'm off by a good margin over here in estimating the atomic mass here. But my guess is in the actual JEE mains paper, they probably would have given the atomic mass for barium here. So if it is 137 here, barium sulfate, let's have a look at that guy directly over here. So barium sulfate, 1 gram is given here. So if it's 1 gram over here, maybe I should duplicate this one again so that I don't have a problem in the next page again. Okay, so barium sulfate here, let's continue on. So 1 gram is going to be given over here, molecular mass of barium sulfate. Let's quickly get that done. So it's going to be 137 plus sulfate is going to be 96, I think, because it's going to be 32 plus 64, 96, yeah. So 96 plus 137, so it's going to be 133 plus 100, so 233. So it's going to be 233, so 1 gram implies it's going to be 1 divided by 233 moles. So that many moles of sulfur are present, sulfur atoms are present, that is present in 0.7 grams. So sulfur atoms means we can multiply it by 32 because atomic mass for sulfur is 32. So this many grams of sulfur in 0.7 grams of organic compound. So now it's all about finding the percentage of the sulfur over here. So if I have to find the percentage of sulfur here, it is going to be 32 divided by 233. This is the actual amount present divided by 0.7 into 100. That is going to be the percentage over here. So let's calculate that off. So it works out as 32 divided by 233. Because we have to sit and solve this as close to accurately as possible, or no need to go too accurate actually, because they have given decently spaced values here. So 32 into 233 multiplied by 100 divided by 0.7. Because the total mass of the substance is going to be 0.7 over here. So we're going to be having 0.7 grams being taken over here. So let's directly go for that now. So in this particular case here, what do we end up having here? So 0.7. All right. So 0.7, let's change it into a 7 over here. So if I'm going to be changing it into a 7, I'll have to put it as another 10 over here up here. So we end up having 32 by 233. 32 by 233 is going to be approximately how much over here? Now, when you're having these kind of calculations here, it is best to basically go directly and approximate off. So let me just do the direct approximation. So this works out as 32 divided by 7. That is the easiest one because it's going to be 28 and then 35. So 28 and 35 means it's going to be 28 4 by 7. Now there is a nice approximation for 7s which you can use. 1 by 7 is 0.142857, which means you're going to be having in this particular case here 1 by 7 is 0.142857 means you will have 4 by 7. It's going to be 142857 bar. The same thing will repeat. So if I'm going to be considering 4 by 7 here, you have to pick the next number. So 1 by 7 is this, 2 by 7 will start from here, 3 by 7 will start from here, 4 by 7 will start from here. So it's 0.571428. So it will be 0.57. That is 4 by 7. So this and this can cancel off, which will give me 4.57. So it's 4.57, 233. So 4.57, 233 means 4.57 into 1000. So let me remove this off. So 4.57 into 1000 works out as 4570 by 233. Now 4570 by 233. Now the real question is it going to be 14 or 19? That is the only idea to pick over here. So look at the answer here. It is 233. So let's say 233 into 2 works out as 466. Whereas 233 into 2 minus 100 and around 16, because you're going to be having half of that you have to take out. So this is definitely going to be closer to 19 rather than closer to 14. So the best answer in this case would be option 1 here if we are to pick the answer among the 4. If this is given as a numerical, no escape, sit and solve. So if you have to pick the best answer among the given over here, definitely the answer is 19.61. Let me just check out the keys of the major players who put out questions and see if they have gotten, if we have gotten this correct over here. Because ultimately a check is always going to be necessary to confirm this kind of a thing, especially when I'm putting up an answer key out over here like this. Guesswork is going to be something which is very useful for getting the most accurate answer when you are given random options like this. So in this particular case here, if I have to guess here for this, I will be picking the answer closest to 19 over here. Question is given differently in different papers. Alan has got a slightly different question. Akash has got a different question. Narayana has given a slightly different question. So I will stick with my answer over here. This is the best approach for this particular question over here. And then they have given the barium atomic mass as well. So yeah, as I had guessed, atomic mass is usually going to be given in these kind of questions. So let me duplicate this guy also so that we have more space. Okay, statement 1, electric discharge is passed through hydrogen gas. Okay, hydrogen dissociates into hydrogen atoms, and the energetically excited atoms emit discrete frequencies. This is a good question, a final question from atomic structure. So this is going to be a question on hydrogen spectrum. Alright, so what is going to be happening? You're going to be having some of the energy is going to be used to break the hydrogen molecule into hydrogen atoms. And then these atoms gain extra energy to become hydrogen excited atoms. This is going to be ground atoms, then they become excited state atoms. Once they have gotten excited, what is going to be happening? They are going to be emitting some discrete frequencies. So when they come back down to ground state, they are going to be emitting some frequencies over here. That is what is going to be happening in this process. So let's have a look now. Frequency of second Balmer line of helium plus is equal to first line of Lyman series of hydrogen atom. Okay, this is going to be a fairly straightforward thing. So emit discrete frequencies. Statement 1 is definitely correct. So statement 1 is correct over here. No problem about that. So statement 1 is incorrect, is not possible over here. Both statements are incorrect is also not possible over here. So electric discharge, when it is passed through hydrogen gas, it dissociates into hydrogen atoms, and the energetically excited atoms of hydrogen do emit specific frequencies once they have become excited, and they get de-excited and fall back down to ground state. Okay, so in this particular case here, when this is happening here, we are definitely going to be having emission spectrum of hydrogen seen. So frequency of second Balmer line. So second Balmer line, let's see what that really means. So second Balmer line of helium plus 1. Alright, so the energy of this second Balmer line means it's going to be Balmer first line is going to be n equal to 3 to n equal to 2 transition. So Balmer first line is n equal to 3 to n equal to 2. Balmer second line is n equal to 4 to n equal to 2 transition. Okay, and it is for helium plus 1. So Z is going to be equal to 2. So we can now directly look at the other case over here. What is the other case over here? They have looked at hydrogen plus 1 is equal to first line of hydrogen. So first line of Lyman of hydrogen. So first line of Lyman works out as n equal to 2 to n equal to 1 transition. Alright, so it's n equal to 2 to n equal to 1. But this is for hydrogen atom, where we are going to be having Z is equal to 1 over here. Okay, so let's put them down into a context directly and see what is going to be happening here. So the two lines which we are going to be considering are energy wise. So let's call this as A, let's call this as B. So energy of A is going to be proportional to Z squared by N squared. So it's going to be 4 because it's 2 squared actually. So 2 squared, which we can write as 4 of course. I'm going to put it as 4 into frequency of Balmer second line. So n equal to 4 to n equal to 2 transition. So it's 1 by 2 squared minus 1 by 4 squared. Whereas energy of B is going to be proportional to, in this case, 1 squared multiplied by first line of Lyman. So it's going to be 1 by 1 squared minus 1 by 2 squared. So let's now check out over here. This is going to be proportional to 1 divided by 4. No, not 1 divided by 4, 3 divided by 4. Multiplied by some constant, of course. The constant is going to be the same in both cases. In this case, we end up having, let's put down for this one now and see what we get. So energy of A is going to be proportional to 4 multiplied by 1 by 4 minus 1 by 16. So now we can cancel these guys off. So it works out as 1 by 4. So it's again proportional to 3 by 4 over here. So both of these are the same. So frequencies of both of these lines are going to be the same. Why are they the same? Because energy is proportional to frequency. Energy is equal to h into nu implies energy is directly proportional to frequency. So energy of A is proportional to 3 by 4. Energy of B is also proportional to 3 by 4. Constant is going to be the same constant, which is going to be my energy of one shell, which is going to be 2.18 into 10 power minus 18 joules or 1312 kilojoules, or whatever you can use the constant which you are comfortable with in that particular case there. You can of course use your 13.6 electron volts also, which is the most common thing. So you're going to be having energy is proportional to h nu over here, or energy is proportional to nu, implies both lines are going to be having same energy. Same energy implies same frequency. So in this case here, both statements are correct is the correct answer here. So you're going to be having statement 1 being the correct one here, or not statement 1, both statements are correct. Option 1 is the correct answer here. Okay, all right. Next up, this looks like another proper calculation based question. So let me duplicate this page also. Okay, now we are ready to go. So we are going to be having in this particular case here two solutions, PQ and PQ2. Okay, PQ and PQ2 respectively non-volatile, non-ionizable. Okay, they are non-volatile and non-ionizable. Okay, wonderful. Containing 1 gram of solute in 50 grams of solvent. Okay, they have given Kb value here. Elevation and boiling point is going to be taken, are going to be 1.176 and 0.689 respectively. Calculate molar masses of P and Q. Okay, alright. So in this particular case here, what is the idea here? We will end up having delta Tb being equal to Kb into molality. Correct? This is the idea here. So 1 gram of solute in 50 grams of solvent. So if it's going to be 1 gram of solute in 50 grams of solvent, what is the idea here? Molality can now be calculated now. So molality is going to be moles per kg of solvent. Moles of solute per kg of solvent. So in this case here, they are giving 1 gram of solute in 50 grams, correct? So 1 gram of solute is present in 50 grams of solvent. Clearly they have given solvent, so we don't need to think too hard, directly extrapolate. So I need to extrapolate this to 1000 grams, 1 kilogram, correct? So 1000 grams ke liye I'll end up having some x grams. So let's say what is going to be that x over there? Automatically 50 into 20 works out as 1000, 50 into 2 is 100, into another 10 works out as 20. So we end up having this as 20 grams of solute. Alright, so we end up having 20 grams of solute in both cases. So what is going to be the molecular masses here? So P and Q are basically the masses over here. So let's take it as P and Q itself. So molality in for the PQ fellow here is going to be working out as 20 by P plus Q. Whereas molality for PQ2 works out as 20 divided by P plus 2Q. Alright, so we end up having delta Tb being equal to Kb into that. So let's now look at the molalities over here and the delta Tb's and get the two equations. So we end up having delta Tb in the first case works out, or it is given as 1.176 is going to be equal to Kb value is given as 5. So 5 multiplied by 20 divided by P plus Q. Right, so this is a very nice cutesy value which has been given here. So not really that cute, it becomes very irritating eventually, definitely. Why will it become irritating? Simply because we are going to be having in this case here, the 100 is not going to be multiplied by that. It's going to be what to say, in a divided state over here. So it's not going to be proper here. So we end up having P plus Q working out to be equal to what over here? Well, I can't take it as P plus Q directly here. I'll end up having it as 1.17. Okay, no need to do that. We'll take it as P plus Q itself. So P plus Q works out to be equal to 100 divided by 1.176. Same way in the other side, if I'm going to be doing, we will end up having, it is also going to be 5 into 20 divided by P plus 2Q there. So we'll end up having the second equation working out as P plus 2Q being equal to 100 divided by 0.689. So these are the two equations here. Now what do we do with these two equations here? We will end up subtracting the equations from each other. So let's call this as equation 1. Let's call this as equation 2. If I do equation 2 minus equation 1, what do we end up getting? We get Q is equal to, well, 100 multiplied by 1 by 0.689 minus 1 by, okay, it's gone to the wrong part there. So I should stop over here. I'll put this in the next page properly. So if I'm doing equation 2 minus equation 1, we end up getting Q being equal to works out as 100 divided by 0.689 minus 100 by 1.176. So it's going to work out as 100 into 1 divided by 0.689 minus 1 divided by 1.176. So this gives me the value of Q. So if I get the value of Q, am I going to be getting the answer directly? Unfortunately, we are having, these two values of Q being the same. That means we will still have to calculate for P over here. But let's confirm if that 25 thing works out over here comfortably or not, or is it going to be too much of an approximation. So let's check if the approximation for that is going to be correct. Because if we get Q as either 60 or 75, our question is done. We don't need to waste time anymore. So in this particular case here, let's check out for 25 first. If it is matching up, then we'll have to sit and solve for P. No options there. So 100 into 1 by 0.7. So let's do some approximations here. There is no escapism here. Approximation is the best way here. So 100 into 1 by 0.7 minus 1 by 1.2 approximately. So if it's going to be 1 by 0.7 and 1 by 1.2. So we'll end up having this as 1.2 into 0.7 works out as, 0.84 actually. So it works out as 100 into 1.2 minus 0.7 works out as 0.5. So it's 0.5 divided by 0.84. So 0.5 by 0.84 means it comes out as how much over here? This is not going to be that bad. This is definitely going to be a much higher percentage here than 25. So it's going to be definitely not these two answers here. It is not 25. So it's one of 60 or 75, which makes our job much more easier. So now let's just calculate out 0.5 by 0.84. 0.5 by 0.84 means that's going to be, well, no need to think too hard. So it's 50 by 0.84. So 50 by 0.84. Yep, it's going to be approximately around 16% more or 16 to 20% more. So answer has to be closer to 60 over here. It cannot be 75 because if we are going to be having it as 75, it should be 50 by 0.75 or 0.6. Because if it's going to be 50 by 0.84, it is definitely less than 50 by 0.8. That is easier to find here. So let's find that out first. So 50 by 0.8 we can calculate and compare. When you're going to be having complicated comparisons, it's always easier to bring it to something which is an easier way to solve and then proceed. So 50 by 0.8 is going to be greater than 50 by 0.84, correct? 50 by 0.8, let's see, 50 by 0.8 will be 500 by 8, meaning we can now take this as 2. So it will work out as 125. I'm dividing by 4 by the way. So 125 by 2 works out as approximately 62.5. Right? So 62.5. So this is going to be greater than 50 by 0.84. So the best answer here is option 3. So answer has to be option 3. We can directly proceed and go off over here. Pay attention to how I'm solving here. I am not sitting and solving and I'm not sitting and wasting time on all the calculations perfectly. I am using approximations very carefully in a sensible manner to get my job done in a way in which I am getting the correct answer. Of course, this is provided I'm given options to pick over here. If I'm not given options to pick, nothing can be done. You can't do any, guesswork like what I'm doing. You'll have to sit and solve. Next one, 1 mole of a gas. I'm assuming ideal gas over here. We cannot do much if it is not an ideal gas. So we can only proceed for an ideal gas and do this kind of thing. Is going to be undergoing following process. There are 4 different processes. They are asking in which of the following work done by the gas is maximum. This is one of those questions which looks very complicated but is actually very cheap. So directly get this done here. Work done in this case here is going to be in the first case is just area under this graph over here. Area under this graph over here. Area under this full graph over here. And here 0. Why? Because area under the graph is not applicable here. So in all of the cases it's 1 to 2, 1 to 2, 1 to 2 and 1 to 2 up over here, 1 to 2 up over here, 1 to 2 up over here. Just looking at the graph doesn't give you the answer. You have to make sure the parameters or the constraints x and y directions are also the same. So in this case, of course, area under the graph is maximum for 3. Why? Because work done is going to be nothing but area under the graph. So when it is going to be area under the graph, ideally, I would highly recommend you check it once that these coordinates in x and y dimensions are all proper. If they are not going to be proper, you'll have to use that also into consideration to get your answer out. Okay. Next one, for the reaction A2 plus B2, okay, this looks like a complicated one, so I suppose I will require another page here for sure. Okay, alright. So for the reaction A2 plus B2 is going to be giving me 2AB. They are giving me some equilibrium constant, okay, at 500 Kelvin. So 500 Kelvin is a critical point to pay attention to. It's done at 500 Kelvin, okay. They give me enthalpy of formation and entropy of the formation of each of the substances here, okay. Calculate the value of X. Okay, they have not gotten this done. Okay, that means we'll have to do it in this way here. So we'll have to calculate delta G naught of the reaction as minus RT ln of K. Alright, they have given us log K over here. So you have to do delta G naught is equal to minus RT ln K. And then say this minus RT ln K is also going to be equal to delta H naught minus T delta S naught of the reaction. So if I can do it in that fashion, I'll be getting the answer properly here. So first I need to calculate this minus RT ln K part here. So let's get this done out over here. So minus RT ln K here, temperature is given, R we know, R is going to be, of course, in this case, since it is in joules, we have to take it as 8.314. So we get it as minus 8.314 multiplied by 500 multiplied by ln K. Ln K means we'll have to convert it to log now because you have been given log over here. So it's going to be into 2.303 into 2.2. This is going to be in joules right now. But pay attention to this part over here. You're going to be having this given in kilojoules here. So you'll have to convert it to kilojoules or you'll have to convert that side to joules there. Easier to always convert this guy into kilojoules over here. So we'll end up having in this case here divided by 1000. Why am I doing divided by 1000? To convert it into kilojoules directly over here. So this is going to be this part over here. Okay, next up. Next we'll calculate for this delta H naught and T delta S naught here. So delta H naught, it will be easier to calculate delta S naught over here. So we do that calculation first because delta H is going to be having a variable there. So delta S naught for the reaction is of course going to be S of products minus reactants. So this works out as, in this case, products are 2 moles of AB. So it is 2 into 240 minus, I'm going to be having 224 minus 238. Okay. So 2 into 240 minus 224 minus 238 works out as 16 plus 2. So 16 plus 2 means 18. Why did I say 16? Because 240 minus 224 is 16. 240 minus 238 is 2. So 16 plus 2 works out as 18 over here. So S naught of the reaction is done. Delta H naught of the reaction, let's just plot that off also over here directly. So delta H naught is again products minus reactants. So if it's supposed to be taken as products minus reactants, products is 32, reactants are 6 and X. Okay, so it's going to work out as 2 into 32 minus 6 minus X. Okay, all right. So this is going to be the case here. So now let's put it up into the final equation. So we end up having, okay, so we end up having 2 into 32, which is 64. So let's put it out directly. 64 minus 6 minus X minus temperature. I need to now include temperature is given as 500 Kelvin. So delta H is this minus 500, delta H minus delta S, minus T delta S over here. So delta H minus T delta S works out as minus 500 into delta S over here is 18 in this particular case here. So if it's 18 minus 500 into 18, which we can add as 9 into 1000 approximately, doesn't make a difference. But remember, again, this is in joules over here. What is the difference over here? I am taking everything in kilojoules now. So should I put it as 500 or should I put it as 0.5? So I should not be putting it as 500, I should put it as 500 by 1000 over here. So this is going to be equal to whatever we got in the delta G calculation. Let's put this fat number out there. So we end up having 8.314 minus 8.314 into 500 by 1000 is 0.5 into 0.5 into 2.3 into 2.2. Okay, unfortunately there is no shortcut here. We'll have to sit and solve this. So we end up having in this case here 64 minus 6 minus X. So we can write it as 58 minus X. So 58 minus X minus 9 is going to be equal to minus 8.314. I'll make it 8.31 into 0.5. 0.5 means we'll just remove that also. We'll take it out more easily. So we get it as 0.5 into 8.3 now. So that's 4.15, make it as 4.1, well, 4.16 is okay. because I'm going to approximate down on that side, so we'll make this higher here. So approximately 4.16 multiplied by approximately 2.2 squared or 2.25 squared. So if it's going to be approximately 2.25 squared, 2.25 is going to be, well, another irritating number there, but it is 1000 by 4, 1000 by 4, 1000 by 8, 1000 by 4 is 250 unfortunately, so it's not 1000 by 4, it's 900 by 4. So unfortunately 9 by 4 whole squared into, yeah, 9 by 4. So 9 by 4 whole squared can be taken easily, 9 by 4 is easier. But similar to, let's look at the options here first. The options are well spread apart, no need to sit and solve perfectly, easier to approximate. So 58 minus 9. 58 minus 9 works out as, well, 47. No, 58 minus 9 is, yeah, 47. No, 49. So 49. So we take x to that side. So x works out as, in this case, I'll bring this to this side. So it is 49 plus, we are going to be having something like this, 4.16 into 2.25 whole squared. That is the value of x approximately. So 49 plus this. So directly we can rule out some options here. 3 is ruled out. 4 into 2. 2.25 whole squared is going to be 2.25 into 2.25. It's definitely going to be above 4. So this value is going to be definitely above 4 over here. So this is going to be greater than, well, 16 to 17 plus. So greater than 17, definitely make it greater than 18. So if it's going to be greater than 18, so in this case we are going to be having it as greater than 4. Obviously this is also ruled out now. So the only options are going to be 70 and 80, which are going to be in our domain over here. So it's going to be 49 plus, well, if I'm going to be having 5 squared is 25. So 25 is not going to be that much further apart here. It is not going to be more than 25, because it cannot be more than 25 here. It is going to be less than 25. So if it's going to be less than 25, so it's 49 plus something less than 25, but mostly something greater than 18. So, well, answer has to be 70. It cannot be 80. Answer has to be 70 in this particular case here. Now again, let me just confirm if this guesswork is correct over here, because ultimately one has to be relatively sure about these kind of questions at least. 70, yes, this is fine. So guesswork is working out over here nicely. So as you can see here, approximations are a very useful tool in a JEE main style exam, especially when you are going to be given options. When you are not given options, no escape. Compound P, when passed on from ammonia and heating, gives compound Q, which is further treated with KOH Br2, gives compound R. With molecular formula, find the correct structure of P. Now in this particular case here, you can do nothing about this. You'll have to sit and check for each of the options. So let's start off with benzoic acid, because 3 of the options are giving P as benzoic acid. So let's start off with benzoic acid and see what we end up having. So if P is benzoic acid on treatment with ammonia, so let's say P is benzoic acid. I should take another copy of this for sure, because we are going to be having another question of the same type, means it's going to be requiring probably one more page. So yeah, so I'm going to be having in this case here, if P is going to be benzoic acid, what do we get here? On treatment with ammonia, we end up ammonia and heating. So we'll end up getting benzamide there. So benzamide is going to be C double bond O NH2. So this will be compound Q. On further treatment with KOH and Br2, what do we end up having? KOH and Br2. This is going to be your Hoffman bromide reaction. So Hoffman bromide reaction, we'll end up getting aniline as the product here technically. So we'll end up having in this particular case here benzoic acid, benzamide and aniline. This seems to work out nicely. Benzoic acid, ammonium benzoate, wrong. Benzene, wrong. And we are going to be having ammonium benzoate, no chance. So answer has to be option A here straight away. So we don't need the second page there. So this question was much easier than I expected. So it's a very straightforward question. So Q is going to be this, R is going to be this. What is this reaction called? This is going to be your Hoffman bromamide reaction. So Hoffman bromamide. It is a named reaction from amines chapter. No escapism, you need to know the reaction. And you need to know the mechanism also if you are looking from a JEE Advanced perspective. But I'm not interested in the JEE Advanced thing here. I'm going for mains right now. Alright, so Next up, again I'll require another extra page mostly, so let me take the advantage and not screw up. Okay, all right. An alkene C4H8. Okay, so alkene is going to be C4H8 in this case here, gives optically active product Q. Okay, that doesn't make sense. Which further reacts with ammonia and gives R. R reacts with this followed by hydrolysis gives S. Okay, so in this particular case here, they have not mentioned what it is reacting with, but we can see here you are going to be having all of them are halogen derivatives. So if they are halogen derivatives, we can say that P is treated with HCl in this case here, because you're going to be doing some kind of an HCl addition here, because you're having only one chlorine there, not two. If we did chlorine gas there, we should have had, well, two chlorine atoms there. That means this question is not fully complete here. Gives optically active product on HCl addition. That is the extra bit which this I think looks like I picked this question paper from Alan's question paper there. They have missed out on it. Small mistakes, it's okay. In the question over there, JEE mains I'm assuming should not have made this mistake. And remember, this is not something which is that easy to do. Alan has actually sat and gotten the question from students directly by word of mouth and then collected and typed it and then put this. Fantastic, phenomenal work, honestly. So yeah, hats off. I had picked it from, I had picked the questions mainly from 3 papers actually. Alan I had checked, Akash I had checked, and Narayana has also had checked. So yeah, maybe I'll do for the next paper from Chaitanya also included and see if any further working out can be done like this. Because ultimately when you check multiple papers, all the any small issues which are there can be automatically worked out and removed off there. Okay, so we're going to be having C4H8 plus HCl. So what do we end up having here? It gives optically active product. So optically active product, this is not optically active, this is optically active, this is not optically active, this is optically active. Okay, all right. So in this particular case here, what do we end up having? This is possible, yes. This is possible, yes. But we have already ruled out, the last, the cases over there anyway. So we have ruled out option 3 and we have ruled out option 1 because second product is not going to be optically active there. Okay. Which further reacts with ammonia to give R. R then reacts with NaNO2HCl followed by hydrolysis. So we have now got option 2 and option 4 as the only possibilities left over. So let's see what we end up having over here. In option 2 and option 4, what are we going to be having? Reacts with ammonia to give R. Okay, when they are reacted with ammonia, they are both going to be giving the amine over here. So amine in this case, this is a better amine. This is not going to be formed. So by just process of elimination, we can get the answer out straight away. Answer has to be option 2 in this particular case here. So why do we get it as option 2 over here? Because let's say I take any of these alkenes, either this or this. Both are going to be giving me the same product here, which is going to be this guy. This is going to be a chiral carbon. So it has to be directly option 2 or option 4. We can eliminate out. Now between option 2 and option 4, when you're picking, when you're going to be reacting it with ammonia there, this with ammonia will end up attacking only on that location. So we'll end up getting product only at that location. We will not get some extra location product. So when I'm hitting this with NaNO2 and HCl, we'll end up getting alcohol formed at that location only. So in this case, best answer is going to be option 2 by a simple process of elimination. No need to think too hard over here. So again, I didn't need the extra page there, but cool, no problem. That's good. Now, this is a question from chemistry in everyday life and not chemistry in everyday life. This is a question from biomolecules chapter, amino acids. Tryptophan and arginine are going to be essential amino acids. Okay, this looks like this is correct. This is a statement which is correct. Glycine has no chiral center. This is also correct. My memory is not that good over here. So I will probably have to confirm for one of them. Proline though I know does not have a 6-membered ring. It has a 5-membered ring. Doesn't have a 6-membered ring. Cysteine is an amino acid having sulfur atom. Now this is something which is very important from a biological perspective. Mainly because when you're looking at beta structures for long chain amino acids, you end up having something like this, correct? You end up having beta pleated sheets which are going to be formed. So when you're going to be having these beta pleated sheets here, pay attention to this part. This is going to be a theoretical analysis there. You are having a 90-degree turn here and a 90-degree turn over here. 90-degree turns are going to be possible only when bond angle is 90. That bond angle is going to be 90 only when it is going to be a sulfur present over there. Think about it. Hydrogen sulfide, bond angle is closer to 90. Why? Because you're going to be having two lone pairs and sulfur is a very large atom. So it's going to be, when you go down the group, bond angle comes closer and closer to P2 hybridization, which works out as closer and closer to 90-degree bond angle there. So sulfur is necessary for the bond angle to be 90 there. There are only two amino acids which contain sulfur, which are going to be cysteine, spelling might not be correct, forgive me for that, and methionine. This part I remember. So definitely this is going to be correct over here. Whereas option C is wrong. So we should be having C correct is wrong. C correct is wrong. D has to be correct. So answer is ABD. So answer has to be ABD. I'm not sure about option A here. That is the only option I'm not sure about, because tryptophan and arginine, I'm not 100% sure if they are essential. My gut feeling tells me they are essential because we eat them. Tryptophan is going to be something which is going to be in chicken usually. It is a very good source of tryptophan. It is a good protein which helps in muscle building. So that part I remember. So if it is present in chicken and we consume it, that means it's definitely essential. We have to bring it from outside our body. It is not non-essential. Non-essential is produced in the body automatically. Essential has to be taken from outside. So in this case here, I was not 100% sure of option A there, or statement A there, but elimination gives me the answer straight away because I knew for sure about option B, C and D. When you are given this kind of a thing here, guesswork is possible, but do not guess randomly. You have to know for a few of the options at least. If you do not know for a bunch of the options, guessing will not help. Propanal and propanone are functional group isomers. Okay, propanal and propanone. Yeah, they are going to be functional groups isomers, no problem technically. Why? Because propanal is going to be this guy and propanone is going to be this guy, which is my acetone. Of course, you're going to be having them having same molecular formula. They are both having different functional groups. One is an aldehyde, other is a ketone. Ethoxyethane and methoxypropane are metamers. So ethoxyethane is going to be this one here, and methoxypropane is going to be propane with a methoxy. So yes, they are metamers. This is also correct. So option B, statement B is also correct. Okay. They're asking identify the correct statement. So let's just finish off everything here and see. Butene shows optical isomerism. So butene is going to be this guy. It can show cis trans. It does not show optical. Alright, optical is not possible. Geometrical is possible. No optical. Alright, so this is wrong. Butene and but1 are functional isomers. No, they are not functional isomers. They are going to be positional isomers, not functional, because functional group here is a double bond. They are not functional. Pentane and 2,2 dimethyl propane are chain isomers. So pentane is going to be what over here? Pentane will be 1, 2, 3, 4 and 5. Okay, 2,2 dimethyl propane. Propane 2,2 dimethyl. So yes, long chain is this, long chain is this, are chain isomers. This is correct. I'll use a different color here. So this is correct. So which statements are correct here? A, B and E are correct. So the correct answer here is A, B, E are correct. You are not going to be having C and D being correct. C and D are wrong. Okay. Next one. This is going to be an organic chemistry question again. So organic chemistry seems reasonably comfortable in this paper. It doesn't look too complicated. Physical chemistry had a good bit of calculation already in the single option correct. Let's have a look at it when we get to the actual questions where there is going to be proper calculations, direct calculations necessary. Compound A gives positive iodoform test but negative tolerance test. Okay. Acidic hydrolysis of A gives product P, which gives positive tolerance test. Okay. And also positive iodoform test. Compound A can be. Okay. So in this case here, we'll have to sit and perform the hydrolysis of each of these here and check it out. So this is an aldehyde over here. Option 3 doesn't seem to be sensible here, mainly because hydrolysis of A doesn't do anything over there. So if this is compound A, so I would not go for option C over here tentatively, but we'll check for the remaining 3 and then come back to option C. Okay, so we are going to be having in this case here, okay, pay attention here. This is going to be something which is going to be an acetal. So there is hydrolysis possible here. This is also an acetal, so hydrolysis is possible over here. So we're going to be having Both of these fellows here, hydrolysis is possible, whereas we are going to be having no hydrolysis possible for this option 4 here. So let's look at compound 1 and see what we get over here. It gives positive iodoform. So to give positive iodoform, let's check out compound 1 first. So I suppose I will duplicate this page first, because that's going to be necessary for the next page for sure. Duplicate it. Okay, now, so we're going to be having in this particular case here, compound 1, let's see. So we have CH3, C double bond O, and a C and a C, and then we have another carbon here, and then we have OCH3 and an OCH3. This is called as an acetal when you are having two OR groups present. So this will undergo hydrolysis comfortably. But first let's check out the test here. So you're going to be having this. So you'll end up having this kind of a group present. So positive haloform, no problem. Positive haloform is tick. But negative tolerance. So negative tolerance means, what is the idea here? This is supposed to be a ketone here. So this is giving negative tolerance. So negative tolerance, no problem, good. Now, when we perform hydrolysis, what do we end up getting over here after hydrolysis? After hydrolysis, we'll end up getting in this particular case here, these two fellows will go away. This will become a ketone type of group over there. You'll get an aldehyde or keto there. So we'll end up getting C, C double bond O, C, C, another carbon, and we'll end up having a double bond over here. Now, this, they are telling me, gives the product P. So this is my product P. This is going to give positive tolerance and positive iodoform. Now in this case here, this will give positive iodoform because these two sides are perfectly fair still, no problem at all. Haloform will be given. So positive haloform is true. This is correct. But it gives negative tolerance. It doesn't give me positive tolerance here because there is going to be only ketone groups here. There is no aldehyde group over here. So option A is not correct. Option A is not correct. Okay, all right. Delhi also we can rule out because there's going to be no hydrolysis here because it's not an acetal. So no hydrolysis happens here. So straight away we can rule it out. So why is this wrong? No hydrolysis. So they are both the same compound. So no meaning there. This also no hydrolysis. That's why it's also going to be out. If it is doing no hydrolysis, then compound A and compound P are same. They should not give me different tests. If they are giving me different tests, that means hydrolysis, some reaction is happening there. So let's look for compound 2 now. Compound 2 is this guy where we are having a hydrogen over here and then an OCH3 and an OCH3. So this on hydrolysis will give me C, C double bond O, single bond C, H and then a double bond O. So now pay attention here, this is going to be an aldehyde. So because this is an aldehyde, I will nicely have tolerance happening over here. So this will give me positive tolerance. So this is compound P, it gives me positive tolerance, and at the same time this part is unaffected. This part will give positive haloform. Whether it is this compound or this compound, both will give me positive haloform. So correct answer for this is option 2. Okay, alright, now next up. Now, which of the following compound is paramagnetic in nature? This is going to be something we have seen in many of those places. In 2 questions, same type of stuff was taken. So I'm not going to be discussing this in too much detail now. So if I'm going to be considering nickel 2+, this is going to be D8. If it is going to be strong ligand, it will be diamagnetic. And it will end up having pairing up happening. It will also be what? In strong ligand, it will be DsP2 and it will be square planar. Okay, I don't need to write in such cramped manner here. I'll write it properly, patiently. So it's going to be square planar. Whereas if the same D8 is going to be in weak field or weak ligands, what will happen? This will be paramagnetic. It will be sp3 and it will end up being tetrahedral. So which ones will come into the pink category here? We'll end up having NiCl4 times 2-. That will be in the pink category, which will come into the blue category there. We will end up having, what to say, it is not just D8, D10 also, same nonsense there. Okay, D10 is not fully same, so I should not put it as same. So in this category, we will have NiCO4 times. Not CO, damn it, sorry, my mistake. NiCN4 times, 2-. Now this NiCO4 is going to be D10 though. D10 is going to be sp3 and strong ligand. And of course, it will also be diamagnetic. So we are going to be having paramagnetic here. So this is not correct. This is not correct. NiCl 4 times 2 minus. We have already seen this is supposed to be correct. We'll just confirm for the last fellow here. Cobalt 3 plus. Cobalt 3 plus is going to be a problem, I see. So iron is going to be iron 2 plus, cobalt 3 plus. So cobalt 3 plus is going to be D6 configuration. All right. So if it's going to be a D6 configuration here, well, D6 configuration usually will have one complication there. It can be inner field. If you are having something which is going to be, well, stronger field or moderate field usually. So in this case, this is going to be something which is technically going to be a complication here, and it should have been COH2O 6 times here. It should not have just been COH2O 3 plus. It should have been COH2O 6 times 3 plus. But small errors is okay. So in this particular case, if it's going to be a D6 complex here, ideally speaking for cobalt 3 plus, I am not 100% sure there, because if it is going to be even slightly stronger, slightly moderately stronger, yes, inner field is going to be fine. But cobalt 3 plus D6, there are many D6 possible. Alright, when it comes to the D6 complexes here, you end up having different types of D6 complexes possible. You have for iron 2 plus, you have cobalt 3 plus, and you end up having nickel 4 plus. All three of these are D6, iron, cobalt and nickel. So when you're going to be having the central system becoming more and more charged, more and more smaller, then it will pull the ligands even more closer. If it pulls the ligands even more closer, then it will be, even with a weak field, it will give me inner. So iron 2 plus, only with strong ligand, this will be diamagnetic, and D2sp3. D2sp3 means inner orbital. Cobalt 3 plus though, with moderately strong and with strong, it will give me the same thing. Alright, so usually in this case, the boundary is going to be water over here. So I would say water and stronger will give same D2sp3 and diamagnetic. Weaker than water, will give sp3d2 and paramagnetic. Nickel 4 plus though, even with weak fellows, even with something like fluoride ion, which is a very weak ligand, this will still be D2sp3. Why? Because the nickel 4 plus is going to be a very tiny system because of the very high charge. So it will pull the ligand very much closer, which will mean that you're going to be having very high field splitting happening. If you're not familiar with what that means, I'll make a video on it sometime later. You can check out my YouTube channel for that. So you'll end up having, in that particular case here, with F minus itself, with a very weak ligand itself, nickel 4 plus will end up giving you inner orbital complex, which will work out as diamagnetic. So in this particular case here, cobalt H2O, this is a borderline case over here. So in this borderline case here, yes, we can say it is going to be D2sp3 and inner orbital. Why? Simply because they have given something which is definitely going to be paramagnetic here and is not going to be a possibility at all, which is option 3. So option 3 is the best answer in this particular case here. Which of the following is the least stable resonating structure? A much more relatively easier question, hopefully. But this is a question where controversies can happen. So in this particular case here, all of them, it is nitrogen plus, O minus, nitrogen plus, O minus, nitrogen plus, O minus, nitrogen plus, O minus, O minus. Okay, all right. So all of them are relatively okay. Relatively okay. All right. Now let's look at the other scenarios over here. They're asking least stable resonating structure. Okay. So if I'm going to be considering the least stable resonating structure, in this particular case here, carbon is having a positive and carbon is having a negative. So carbon having a negative is not that good. Carbon having a negative is not that good. Carbon having a negative is not that good. So we can rule out the last option, because oxygen is having a negative, decently good, no problem. Okay. Next up, we are going to be having, in this case here, we are going to be having a negative charge here is closer to this pi cloud over here. All right. So negative charge is closer to this pi cloud, and the positive charge and positive charge are going to be close by, which will cause more repulsions here. So this is going to be high repulsion case. So this is going to be a case which is going to be having high repulsions. So this is a complicated one, a more trickier one. Whereas in this other here, you are going to be having, why is this high repulsion? Because lone pair over here and this pike load, repulsion here and repulsion there. Positive and negative charge and what to say, pike load are both going to be repelling over here. In this case over here, it is bit more easier to look at. So this is more comfortable because this can still shift over here. Negative is closer to positive, positive is closer to pike load. So this is definitely better than that. So we can say option 4 is best. 4 is most stable, so I'm not going to consider 4 here. 3 is more stable than 2. More stable. I mean, stability order I'm putting here. So now the last one to check is going to be option 1. Option 1 is not that bad. Yeah, you're going to be having repulsion slightly, but the positive repulsion is not there. So option 2 is the worst here. Option 3 is not that bad. So I will definitely say it like option 1 is going to be more stable than 2. So 2 is going to be least stable here. So if I have to pick an answer here, I'll be picking 2 as the least stable here. So 2 should be the least stable one in this particular case here. 2 is least stable. Why is option 2 the least stable? Look at the stabilities, look at where the negative charges are. So first I did what? I checked out where the negative charges were. Negative charge on oxygen is better. Positive charge is going to be only on nitrogen with octet in all places, and positive charge is going to be on carbon in all the cases as well. So everywhere it's the same thing. So nitrogen, everything is having octet, no other complications there. Excepting carbon plus in each case, everything else is having octet. So among them then, every one of them is having only one atom without octet, which is carbon. Then we check for where the repulsions are going to be greater. Repulsions are going to be greatest in option 2. Why? Because in option 2, you're going to be having lone pair and negative charge. Lone pair on the negative charge and the pike load are both going to be close by. So repulsions there. Positive charge on the carbon, positive on nitrogen also going to be close by. Repulsions over there. So you'll be having this as the scenario here. Okay, now we are finally into the, numerical questions. So I suppose I'll have to make some extra space here definitely. Numericals deserve the respect definitely. For two chemical reactions A and B, we are going to be having, if the difference between their activation energy is 20 kilojoules, okay, at 300 Kelvin. I'm not going to be taking it at some other thing. At 300 Kelvin we'll take. Determine ln of K2 by K1. Okay, this is a fairly straightforward question here. So we can write like this. So rate constant K1 is going to be A1. Okay, I'm going to assume that we are going to be having, the A1 or the ln of A or the, Arrhenius constant involved there is going to be the same. Otherwise, we cannot proceed here. So we're going to be having it as A e to the power of minus EA1 by RT. So we are going to be having ln K1 can be written as ln A minus EA1 by RT. As simple as that. Similarly, if I'm going to be having same Arrhenius constant A, then only this is going to be applicable. Same type, if I'm putting for ln K2, that will work out as ln A minus EA2 by RT. Okay. If the difference between their activation energy is going to be given as 20 kilojoules. Okay, alright. And we have to find a proper whole number over here, I suppose. So they're asking ln K1 by K2. That's a fairly straightforward calculation then. Or ln K2 by K1 they're asking. So ln K2 by K1 can be written as, let's call this equation 2. Let's call this equation 1. So it's 2 minus 1. So if it's 2 minus 1, it is going to be EA2 minus EA1 divided by RT. As simple as that. So EA2 minus EA1 works out as 20 kilojoules is what they've given us. So 20 kilojoules over here means we are going to be having 20 into 1000 kilojoules. We need to convert into joules, and R into T. R is going to be 8.3 into temperature, which is going to be 300. So cancel off these two, 8.3 into 3. 8.3 into 3 means we're going to be having 8 into 3 working out as 24. 0.3 into 3 is 0.9. So it's approximately 25. So we can say this is going to be 200 by 25 approximately. Now, unfortunately, I'm not sure whether JEE Mains is still accepting integers as the answer, or you need to calculate exactly. JEE Advanced definitely requires exact calculation, but I'm assuming JEE Mains is only wanting integer answer here. So it is going to be approximately 200 by 25, which should approximately be equal to 8. So approximate answer will be 8 in this particular case. No complicated extra nonsense is required if you can put integer answer. But if it is not an integer question, you'll have to sit and calculate the exact value. 8.3 into 3 is 24.9. So 200 by 24.9 you'll have to solve. No options there. No escape there. Okay, all right. Okay, so this question worked out in one page itself. We didn't need the next page. Let's look at this one. 10 moles of oxygen gas is heated at constant volume from 30 degrees to 40 degrees. Change in the internal energy of the gas is what? They're giving a CP. Good people have given a CP. So we know already Cp minus Cv is supposed to be equal to R. They're given R here nicely for that purpose only. So Cp is going to be given as 7. So we end up having Cp minus R is going to be equal to Cv. So we end up having Cv working out as 5 calories wise. They're asking us change in internal energy. Very straightforward. Delta U is going to be equal to NCV delta T. So N is given as 10 moles. So 10 into 5 into delta T is 10. So it's going to work out as 500 calories. So very straightforward answer, 500. Not bad. The numericals are at least easier in this paper from the looks of it. Maybe I counted my chickens too soon over here. This looks like a painful one. Let's see. They're asking find the percentage of nitrogen in the final product. So first we are doing HNO3 and H2SO4. So that's going to be what? HNO3, H2SO4 is going to be nitration or sulfonation? It's going to be nitration. So in this particular case here, we are going to be having NO2. Then we are going to be doing tin and HCl. This is product after first step. After second step, tin and HCl, we'll end up having aniline. Next, after aniline, we are doing CH3COCl. So we'll end up technically having this guy getting out over here. So we'll end up having a product obtained like this. NH C double bond O CH3. Okay, then we are doing HNO3 and H2SO4 again. So when you're doing HNO3, H2SO4, now you'll be doing nitration again. Pay attention here. This is going to be something which is technically going to be a plus R group only. It is not that bad. It is still technically plus R. Yes, it is a weak plus R. Much weaker than aniline over there. Why do you end up doing this? To protect the aniline group over here. So what you're doing here is actually protecting the aniline group here. Let me explain that in the next step over here. So when you're doing nitration again here, what will you be getting over here? We'll get mononitration product. We can have the mononitration obtained NHCOCH3. So we have NHCOCH3. We will have either over here or over here. I don't care where, no problem. But only mononitration, not double, mono product. Mononitration happens. Last step, they are doing hydrolysis over here, H2O bar OH minus. So the final product will be one of two things. We will either be having NH2 and an NO2 here, or we will have NH2 and an NO2 over here. So all we have to do is find the percentage of nitrogen in this final product over here. So I should have copied the page again, made a mistake here. I should have duplicated it in the beginning. So for this question over here, I'm going to leave this particular final calculation to you guys over here. Maybe we can sit and solve it off some other time, but I'm guessing this is not going to be that complicated here. Since I am solving the paper anyway, I might as well sit and solve it fully. So having two nitrogen atoms, so formula finally is going to be C6. We are going to be having H4, H5, H6. So C6, H6, N2 and O2. So C6, H6, N2 and O2. So what is the molecular mass here? C6, H6, N2 and O2 means O2 is 32, 32 plus N2 is 28, so that is 60, 60 plus 72 plus 8, 72 plus 6, 78. So 60 plus 78 works out as 120, 138. So 138. So 138, and we are going to be having 28 over here. So percentage is going to be 28 by 138. So 28 is 28 by 138 into 100. So that is going to be the percentage over here. That calculation I'm leaving it off now. Okay, alright. Next up, we are going to be having NaCl plus K2Cr2O7. I suppose I'll do that calculation also towards the ending after the full paper is completed. I want to leave at least one calculation to the end to see if I'm finishing the paper now. So NaCl plus K2Cr2O7 plus corn sulfuric acid. This is going to be your chromyl chloride test here. So A is going to be chromyl chloride. So chromyl chloride is going to be compound A. So this plus NaOH is going to be giving me Na2CrO4. So this is going to be compound B, and that with H2O2 and H2SO4. This is going to be your test for chromate ion. So this is going to be a question from qualitative analysis finally. I would not say qualitative analysis, hydrogen also has this, but I think hydrogen has been removed from your syllabus. So it's a test for hydrogen peroxide actually. So we'll end up having in this case here CrO5. So technically it's from qualitative analysis, not from that. So CrO5 will form a blue color lake if you are going to be having a proper reagent to form that lake on top of. Okay. Oh, they're asking us some very interesting questions here. Number of O2 peroxide in C. It's a very weird way of looking at it. Number of peroxide link in C they are asking. This is a very awkward way of asking the question. Very weird way of asking the question. So let me just discuss for each of these over here. So we are going to be having oxidation state of chromium in C. That is the easiest. It is going to be +6. Okay, so this is compound C. Oxidation state of chromium is +6 here, +6 here, and +6 here also. Okay, number of oxygen atoms in compound C in Y is equal to Y. Okay, number of atoms in compound C, this works out as 5. Okay, so Y is going to be equal to 5. Oxidation state of chromium in compound C, that is going to be Z. So Z is going to be 6. Okay, all right. Lastly, number of peroxide ions in C. See, CrO5 structure is going to be like this. You're going to be having it as double bond O and O. So technically, if I have to say number of peroxide links, there are 2 peroxide links over here. So I would say this is going to be 2. So X is going to be 2. So X is 2, Y is 5, Z is 6, means we end up having X plus Y plus Z working out as 2 plus 6, 8. 8 plus 5 is going to be 13. So I would say the answer for this is 13. But ideally, I'd have to check this up exactly what they have asked there. They should not have asked this as peroxide ion. They should ask this as peroxy links. Then it is more easier. The fact that they have put 2 minus there, that is where the problem comes. Okay, so this is technically the last question of the paper here which I have. pH and conductance of a standard solution of HX are 5 and 4 into 10 power minus 5 Siemens respectively. Okay, all right. The standard solution is present in a cell having length between electrodes as 15 centimeters and area is 1 centimeter square. Calculate the limiting molar conductivity of the standard solution. Assumed degree of dissociation of HX is going to be very much less than 1. Okay, so this is gone for very long over here, this paper discussion. So I will do this. I will put this solution up separately instead of on this over here alone. This is going to be a bonus question which I'm going to be putting up. No, actually, no, why not? I'll just discuss it off directly. Why should I put it as a bonus question? Let it be a big paper, big video. Chalega. So pH is given as 5 and pH is going to be given as 5. Okay, that means H plus concentration is going to be 10 power minus 5. Alright, the standard solution is going to be present. Let me just check how much time it has gone on in this video here right now, because this is surprisingly very long, because I'm discussing it and solving it at the same time. So in this particular case here, it has already gone for nearly 2 hours. Unexpected, but okay. So pH is going to be equal to 5, H plus concentration is going to be equal to 10 power minus 5, okay. And they are giving us that conductance. Conductance in this case is given in Siemens over here, so this is G. So conductance is given as 4 into 10 power minus 5 Siemens. Okay, alright. Okay, having cell length between electrodes, they are giving us L by A over here. So L is going to be given as 15 centimeters, A is going to be given as 1 centimeter squared. Calculate the limiting molar conductivity of the standard solution. Okay, alright. So how do we proceed over here? So G is given over here and they have given us concentration of this H plus over here. So it's a standard solution. So that means we are going to be having in this particular case here, H plus is going to be 10 power minus 5. That means my X minus is also going to be 10 power minus 5. Technically, concentration of both of them are going to be equal. So we can say H plus concentration and the X minus concentration are going to be the same over here. Now, in this particular case here, if we have to proceed here, 1 minute, I need to check something here. I've just gotten a message in my phone here. Okay, alright, so doesn't make a difference now. I will finish that thing. It is more than 2 hours now. I thought it was some message to confirm if it is basically gone too long over here. So now what is the idea over here? You're going to be having conductance is going to be given over here, correct? So this is going to be given as 4 into 10 power minus 5. Now molar conductance, how do we imagine, what is the best way to understand molar conductance? Molar conductance is going to be nothing but conductance offered. In this case, what are they asking? They are asking you to calculate limiting molar conductivity of the standard solution, which is basically the same as molar conductance at limiting condition. Limiting condition means you are going to be looking at 1 mole of each of those fellows present in that particular scenario there. Alright, if it is going to be in limiting condition, you have to consider it at, what to say, full system is present over there. Now, in this case though, it is not, okay, they are asking for standard solution only. Okay, alright, so molar conductance is going to be effectively going to be nothing but kappa. Kappa is going to be not meaningful here. So let's see over here. So you're going to be having molar conductance. What do we proceed over here as? Molar conductance, yeah, molar conductance, direct definition is best. Molar conductance is going to be the conductance offered when you're going to be having that particular solution of 1 mole in the starting taken over there. Alright, so if you're going to be taking 1 mole at starting, they are telling you standard solution here. So we can assume you have taken 1 mole at starting. So for that 1 mole at starting, you're going to be having it like this. So in this particular case here, if you are supposed to be having conductance to be considered here, you're going to be having conductance is going to be, what is the formula there? Resistance is equal to rho into L by A, right? Or that, sorry, R is going to be equal to rho into L by A, correct. So we are going to be having in this case conductance works out as 1 by rho into A by L. Alright, so 1 by rho into A by L. So in this particular case here, if I'm going to be having 1 by rho into A by L here, how to proceed over here? They are asking meter squared over here. So that is another complication to pay attention to. So in this particular case here, rho is what we have to calculate out over here. We have been given A and L here, so shift it to the other side here. So rho works out as, no, not rho, we'll just call it as 1 by rho there, that is easier to play with. This is going to be kappa. Right, 1 by rho is going to be your, what do you say, kappa over here, or conductivity over here, or specific conductivity in this case here. So we'll end up having, no need to go for this nonsense here, this is not necessary. I'm just using physics terms because chemistry terms become a little bit more complicated and unnecessarily complicated to use over there if you keep changing it from lambda, m, etc. It is easier to use physics terms when you can understand physics part better there. So in this case here, how do we end up getting? We will end up having kappa working out as equal to G into L by A. Okay, so G is given as 4 into 10 power minus 5. So it works out as 4 into 10 power minus 5. But now we have to bring it into meters over here completely. So we'll have to write everything into meters. So it works out as into 15 into 10 power minus 2 divided by 1 into 10 power minus 4. So if I'm putting it up, I'll be getting it as, okay, I forgot to copy question, but sure, it's okay. So kappa works out as 4 into 10 power minus 5 multiplied by 15 into 10 power minus 2 by 1 into 10 power minus 4 multiplied by 15 into 10 power minus 2 divided by 1 into 10 power minus 4. So we'll end up having this working out as 60, and we'll have this and this going off. This will become 10 power minus 1, 10 power minus 3. So we end up getting it as 16 to 10 power minus 3. So it works out as 6 into 10 power minus 2. So this is the kappa here. Now next up over here, what is going to be looked at over here? They are asking us to calculate what is going to be limiting molar conductivity of this fellow over here. So if I'm going to be asked to calculate limiting molar conductivity, Siemens meter squared per mole. Okay, alright. They are given that concentration is going to be 10 power minus 5 there. So pH has been given as 5. That is not particularly useful over here. Assume degree of dissociation is very much less than 1. That means I have to calculate the actual concentration over here then. Okay, so we end up having pH is equal to 5, but initial concentration has not been given. We can take standard solution, means initial concentration is equal to 1. So initial concentration is going to be equal to 1. So we'll end up having, in this case here, molar conductivity is going to be equal to 1000 kappa by C. So in this particular case here, C value is going to be equal to 1000 times kappa by C. So we'll end up having 1000 times kappa by C. C is going to be equal to 1. So no need to bother then. So molar conductivity can be directly written as 1000 times kappa by C, which works out as, in this particular case here, 6 into 10 power minus 2 into 1000 divided by, I'm going to be having C. So this should work out as, is this correct here? Because I'm being very ambiguous here. I'm not taking, I need to consider in moles, no? I need to consider meters. I should be careful about that. So it should not be 1000 times kappa by C. It should be just kappa by 1000 C. I need to take it for 1000 liters, no? So 1000 liters. So I should be taking it for 1000 liters, means limiting is also used over here. Okay, chalo, it's okay, it doesn't make a difference. For the time being, I'll just sort off this question and then we'll proceed on. So it works out as 60 for now. I'm not 100% sure of this question. I'll have to check this out once more here, because there are a lot of, how to say, unit problems over here. Because there's 15 centimeters here. This is in 1 centimeter squared here. We are also having standard solution here. And we are having 4 into 10 power minus 5 Siemens over here. So there are going to be definitely issues for this question here. As of now though, I would say the question's answer is going to be 60 in this particular case here. I will check up this once we have got a proper question available, and of course I also doubt if my methodology is properly correct here. So this one question I'm not sure here. It is mostly going to be 60, but I'll confirm this once we are done with getting the proper question paper out. So this technically finishes the question paper discussion here. Thank you very much, YouTube. It has been a pleasure. And I'm going to be interested in you, anyone who does watch. Please do watch and share, subscribe, and do comment, especially on this last question, which I'm not sure of. And also one more question over there where I did not solve it fully. This one here, 28 by 138 into 100. I didn't solve the thing fully. So if you do have something to discuss on this, do comment on this. I will reply for this definitely. I will check the comments here. If it's going to be question type, I will definitely end up replying it. Take care till then, guys. Thank you very much. Have a nice day. Bye bye. Good night.